Hey everyone, today we're going to move on from calculating areas between curves and we're going to start talking about volumes. And actually we'll be working with volumes for the rest of this chapter. So we're going to be working with some 3D figures now. It may be a little hard at first to visualize actually what's happening. When we're back in class after spring break, I'll show you some things on the computer that'll kind of help make it a little more real, and then you guys will be doing a project that'll definitely help you visualize the type of solids we're creating here. So for now, just bear with me and kind of let's get used to this process, and then like I said, we'll get into more some things that'll help us visualize what's actually happening. So sometimes we can use an integral to find the volume of a solid three-dimensional figure. So remember, integrating is essentially adding together a bunch of smaller units within a certain set of boundaries. So when we've been doing areas, we know we're essentially adding together a bunch of rectangles. So we're going to use that same idea now when we're talking about volume. So what I want you to think about is a loaf of bread. Okay, and so if we were to take a look at a loaf of bread from the top, we would pretty much see just a rectangle. Okay, and we're going to consider that the base of our loaf of bread. So what kind of shape is that sitting on? So that'd be pretty much a rectangular shape. But now if we look from the front, it's going to look something like this. Now don't mind my silly looking loaf of bread, but it's going to be something like this. So if you think of looking at it from the front, or indeed if you cut any kind of slice of bread, it would have this shape. And so that's what we think of as our cross sections. Now, you guys could probably picture, if you think of a loaf of bread, depending on where you are in the loaf, the cross sections are likely going to have the same shape, but maybe different sizes. So in the middle of the loaf, they're going to be bigger, whereas the ends, they might be a little smaller. So I'm going to make a note here. Our cross sections are going to be the same shape, but different sizes. So what I want us to think about, if we could take our loaf of bread and cut it super thin so that each slice was essentially as thin as a piece of paper, that slice wouldn't really have any depth or any thickness. So we wouldn't really think of the volume of that slice of bread, but we'd more be talking about its area. And if we added up all those super thin slices of bread, eventually we would get that loaf or that three-dimensional figure. And so that's kind of the context we're going to be working with here. Taking infinitely slim cross-sections of a solid, but that adding them up so that in total we get the volume of a 3D figure. So for the volume of a solid. Okay, so the volume of a solid of known integrable cross-section areas. So again, if I could find the area of that cross-section, I know to get the volume, I would just add them up. And to add them, we use an integral. So we would integrate, our volume would be the integral from a to b of a of x dx. Right, so this area is the area of the cross-section. Okay, and we know that area is going to depend on our function that's going to be given as our base. So I'm going to say depends on f of x or our base, and we'll get into a little more what that means in a little bit here. Now, we can have two different types of cross-sections. We can have cross-sections that are perpendicular to the x-axis, and if so, we're going to set up our integral with respect to x. So if I have my x-axis here, I might have cross-sections that are going to be perpendicular to x. And again, we'll see what that would look like in a problem. On the other hand, if I have cross-sections that are perpendicular to y, and that would be specified in the problem, then we're going to set up our integral with respect to y. And so we could also have it where we have our y-axis, and now our cross-sections are all perpendicular to that y-axis. And again, that would be specified clearly in the problem. Now, this really all hinges on being able to find areas of cross-sections of different figures. So what we're going to do is we're going to go through formulas for some of the most commonly used figures. Some of these are really straightforward, and some of them are not maybe so common, so we're going to go through how you could derive some of these formulas if you happen to forget them. So we'll start here at the bottom. I'm going to shift up. Okay, so we're going to find the area of the following figures. Now, hopefully, a square is something that we're all very familiar with. For congruent sides, if we call them side length s, we know our area is just s squared. Now, something a little different is a square with diagonals of length d. So let's think about what we have here. I have a square, and I know its diagonal is length d. So let's see what else we know. I know this is a right angle, and by my properties of a square, I know this is going to be a 45, 45, 90 triangle. So if this is a 45, 45, 90, and my hypotenuse is d, I know that my legs are going to be d over root 2. Okay, that's just our 45, 45, 90 triangles. So now my area is still the length of a side squared. The length of one side is d over root 2. So if we square that, we're going to get d squared over 2. So this is, again, something that hopefully you'll memorize as we do these problems over and over again, but you also have a way to derive it if you happen to forget. Okay, now the next one we want to talk about is a semicircle of diameter d. So we need to think about this one. If I were just talking about a semicircle, I know that's a equals pi r squared over 2. However, this is in terms of radius, and we want our formula in terms of the diameter. So I know that radius is our diameter over 2. And I'm going to use that to go ahead now and substitute this so I have a formula that's in terms of d. So what I have is pi times d over 2 squared over 2. So I've got pi d squared. 2 squared is 4. I'm going to multiply essentially by 1/4 on top and bottom, and I'm going to get pi d squared over 8. Or a lot of times I'll just use that as pi over 8 times d squared. So that's our area of a semicircle of diameter d. Okay, the next one, we have an equilateral triangle with sides of length s. So again, let's draw a picture. This is probably not one we have at the top of our heads. And I know these sides, it's equilateral, they all have a side length of s. So now, I have to be able to figure out the area here. Well, I know my formula is going to be 1/2 base times height, but I have to express that base and that height as a function of s. So here's what I'm going to do. I'm going to drop my perpendicular here. So I have a 90-degree angle. If this is equilateral, I know all three angles are also congruent. If it's equilateral, it's equiangular. So each angle has to be 60 degrees. So what I have is a 30, 60, 90. So if this side is s, and that's the side opposite the 90, I know the side opposite the 30 has to be s over 2. Now, my side opposite the 30 is s over root 2. To get the side opposite the 60, I multiply that by root 3. So what I have for the height of my triangle is s root 3 over 2. So now the area of my triangle is 1/2. I know the base of my triangle is s, and the height is s root 3 over 2. So my area formula is going to be S squared root 3 over 4. Again, these are formulas that you are going to have to know. They will not be supplied to you. So whether you memorize them or you can derive them is fine, but you're going to need to know these formulas. All right, a couple more. We have an isosceles right triangle. So let's first think of what that looks like. It's right. Isosceles means my two legs are congruent, and it says my legs have a length of S. So this one is really straightforward now. I know my area is 1/2 times the base of S times the height, which is also S, so I have S squared over 2, or 1/2 S squared. All right, and last but not least, let's see what we have here. An isosceles right triangle with hypotenuse of length H. Okay, so isosceles right. So again, I know if it's isosceles right, I have a 45, 45, 90. If my hypotenuse is H, I know that each of my legs is H over root 2. So now my area is going to be 1/2 the base, which is H over root 2, times the height, which is also H over root 2. And if I simplify that, I get H squared over 4. So those are the area formulas that will be used commonly when we're doing these types of problems. So now that we've got all this out of the way, let's actually take a look and see what these problems are going to look like. Okay, so here's what a problem might look like. It says the base of a solid is the region enclosed by the semicircle y equals the square root of 25 minus x squared and the x-axis. So here is the shape of my base. And again, if you think of that loaf of bread, this is just kind of what is the bottom or the base that this shape is sitting on. I know it's 3D, but what's its base look like? Okay, now we're going to find the volume of a solid whose cross sections are perpendicular to the x-axis, I should say. So we know we're going to set up our integral with respect to x, and now we're going to find that volume if we're given these different cross sections. So here we go. I'm going to get some colors here. So for part A, I want to find the volume of a solid whose cross sections are squares with one side on the base. So here's what happens. My base, we already know, is a semicircle. Squares with a side on the base, what that means is at any point, I have this is a side of my square. And what's really happening is I have all these squares that are kind of sticking up off of the page. So I could draw in a couple. These are all sticking up off of the page so that if I added them together, I'm generating a solid 3D figure. So here's how I kind of approach these problems. I know I have squares, and I know my formula is area equals S squared. So that's the first thing I do is I get my area formula set. So that's kind of my number one. Now the second thing I need to figure out is what is S? Well, I know that S is this segment here. And I can find S just by finding the difference between the top and the bottom. So I'm going to use top minus bottom to figure out S. Well, for me, I know the top is the top of this curve, so square root of 25 minus x squared. And the bottom is just the x-axis, so minus 0. So my S is just the square root of 25 minus x squared. Now, I know that to find this volume, I have to integrate or add up all of the areas. So the next thing I'm going to do is find the area in terms of x. So I know I'm going to be integrating with respect to the x-axis because this is perpendicular to x. So that means my area also better be in terms of x. So I'm going to say area of x. Well, we said it was the side, which I now know is the square root of 25 minus x squared. And we said it's the side squared. So my area now is just 25 minus x squared. So now that I have a formula for area, I can integrate to find the volume. So I'm going to integrate. My limits are going to be from -5 to 5. And I'm going to integrate 25 minus x squared with respect to x. So if we go ahead and do this, my antiderivative is 25x minus x cubed over 3. I'm integrating from -5 to 5. So what I have, 25 times 5 is 125 minus, let's see, I have 125 over 3 minus, now I have a -125. And here I'm going to have a plus 125 over 3. So with some simplification, 125 minus a -125 is going to be plus. So I'm going to get it 250. Now I'm going to have minus. This negative gets distributed to make that a negative. I'm going to have minus 250 over 3. Well, 250 I know is just 750 over 3 minus 250 over 3, which is going to give me 500 over 3. And that would be the volume that I get when I have this semicircle as a base and I build a solid by building squares off of that base. Now, we're going to see how this changes if I now have squares that have their diagonal on the base. So this is different. Before we had squares with a side on the base, now we have squares with a diagonal. And that's why we had all these different area formulas before. So now I need my formula for a square with a diagonal on the base. Well, we said that the area of a square with diagonals of length d is just a equals d squared over 2. Or we can think of it as 1/2 d squared. So now, again, I need to figure out, well, what is this d? And again, since I'm perpendicular to x, the d is still just the top minus the bottom. So in our case, we already know what that was. It's the square root of 25 minus x squared minus 0 because we're on the x-axis. So it's just the square root of 25 minus x squared. So now I can take my area formula and get it in terms of x. I'm going to have 1/2 times my square root of 25 minus x squared, because that was our d. And then I'm going to square that. So I'm going to get 1/2 times 25 minus x squared. Now, I'm actually not going to distribute that 1/2, and here's why. In step 4, when I go to integrate this, I'm still integrating from -5 to 5. And I should say now we're finding the volume. It's the integral from -5 to 5 of my area formula, which is 1/2 times 25 minus x squared dx. But here's what I want us to see. I know I can just move a constant out of that integral. So I really have 1/2 times the integral from -5 to 5 over 25 minus x squared dx. Well, hopefully, we should recognize that we already know the value of that integral. We calculated that up here when we had a square with a side on the base. And we knew that value was 500 over 3. So rather than go through and redoing all that work, I'm just going to use that result. So now I have 1/2. Again, I know the value of this integral is just 500 over 3. So by simplifying, 500 over 2 is 250 over 3. And I should say these should be units cubed because we're doing volume. So you can see if I'm working with the same base and just changing my cross sections, we can reuse these results. So we'll do just a couple more and then we'll save the rest if we need to go over some in class. So let's do part C here. Now we have a semicircle whose diameter is on the base. So we said, let's see, a semicircle of diameter d. We knew that formula, our area, is pi over 8 d squared. Again, d is just our top minus bottom. Same top minus bottom that we've been doing because we have the same base. So our d is going to be square root of 25 minus x squared. Now that I have d in terms of x, I can get my area in terms of x. So that's going to be pi over 8 times d, the square root of 25 minus x squared, and we're going to square that. So I have pi over 8 times 25 minus x squared. And hopefully you can see where this is going. Now we've got our area formula in terms of x, so it's time to integrate, to add up all those areas to generate our solid. So the volume is going to be the integral from negative 5 to 5 of our area formula, pi over 8 times 25 minus x squared dx. Again, we can move a constant through that integral. So what I have is pi over 8 times the integral from negative 5 to 5 over 25 minus x squared dx. And again, there's that familiar integral. So we're going to take the same answer. We know the value of that integral was 500 over 3. So we're just going to take pi over 8 times 500 over 3. And let's see, if we simplify this, we will get, let's see, 500 pi over 24. And I'll simplify that. Let's see, that's going to give us 125 pi over 6. So if I divide by 4, I get 125 pi over 6 units cubed. Okay, so we'll leave that example there. Obviously, we're running high on time, but hopefully you're kind of watching this in stages over break. So we're going to go on now to a new problem that has a different base, so we can make sure we know how to approach this with a new base. And I will warn you, this is going to go, it's already gone over 20 minutes. It might go to 30. I apologize for that, but again, hopefully since you have the time over break, it won't be too bad. All right, so let's look at number 2. So now we have a new base here. The base of our solid now is the region enclosed by negative x squared over 9 plus 4 and y equals 0. So we've got this shape here. Okay, so now we have cross sections perpendicular to the x-axis. Our rectangles, now they're rectangles with heights twice that of the side. So let's see, we said perpendicular to the x-axis. So it would look like this. Again, we're still doing top minus bottom. And then again, we're generating rectangles. So it looks something like this. So those rectangles would really be standing off the page if we could represent that in 3 dimensions. So I'm just drawing a couple to kind of get an idea of what's happening here. Now, this one's a little new because what we have is areas that are rectangles with heights twice that of the side. So let's see, we know for a rectangle we have area is base times height. But this is telling us that our heights are twice that of the side or a base. So we have base, our heights now are really 2 times the base. So our area is 2b squared. So that would really be our step 1. We had to kind of generate our area formula there. Okay, now for step 2, right now if I'm going to get this in terms of x, I need to figure out what b is. Well, again, since we're perpendicular to the x-axis, b is just top minus bottom. It's worth writing that again. So our top is negative x squared over 9 plus 4. Well, our bottom, since it's just the x-axis, is going to be minus 0. So our base is negative x squared over 9 plus 4. So now I can get my area formula in terms of x. We said it's 2 times our base. Well, we have an expression for that, negative x squared over 9 plus 4. And we need to square that base. So there's the area formula that we're going to use to do our integration now. So we can set up our integral, and we'll use our calculator for this. We're going to have the integral from negative 6 to 6. Again, we're getting those limits from the x-axis. And we're going to integrate our area, negative x squared over 9 plus 4, quantity squared dx. And now we're going to use our calculator to get that value. So let's see. I'm going to go Math 9, negative 6 to 6. Got 2 times negative x squared divided by 9 plus 4. That quantity is squared, and this is with respect to x. And we get a volume of 204.8 units cubed. All right, we're going to go through one more so we can see what it would look like to do cross sections perpendicular to the y-axis now. And this will be the last one that we do, so thank you for hanging in here with me. So let's see, they didn't give us the region, but they're describing it here. So let's see what this is going to look like. We have the space bounded by y equals x squared. So let me see, let's get a picture of what this looks like. All right, so y equals x squared. The line x equals 3. And let's see, our other boundary here is the x-axis. So I'm looking for the region that's bounded by all 3 of these curves. So hopefully we can recognize it's this area here. And we want to make a 3-dimensional solid by making cross sections. Now we're perpendicular to y. So instead of doing top minus bottom, really we're going to be right minus left. And now this doesn't specify. It would have to specify what our cross section is. So we're going to say our cross sections are squares we'll just do with a side on the base. So let's kind of go through our steps here. We know our first step is to get the area formula for that cross section. So if I'm squares with a side on the base, I'm going to be area equals s squared. Step 2 is to figure out what s is. Now again, because I'm perpendicular to the y-axis, we're going to be doing right minus left. Whoops, I guess I should put a T in there, and then I can put my exclamation point. So S now is right minus left. So here's what we have to think about. I know my right is just 3. But my left, I have to be careful because right now I have this solved for y in terms of x. But if I'm doing perpendicular to y, I know my integral has to be in terms of y. So I need to solve this. So I'm going to take the square root, And I'm going to have x equals the square root of y. Now, because we're only in this region in the first quadrant, I don't have to consider the opposite of the square root of y. I can just take square root of y. So my left is square root of y. So again, that's my right minus left. That's represented by this blue here. That's my side. So now I can get my area in terms of y. And so it's just side squared. So I have 3 minus square root of y, quantity squared. So now our only job is to set up our integral. So we have the integral. We're going to integrate our area function, 3 minus the square root of y, quantity squared, dy. Now we have to set up our limits of integration. And remember, just like when we were doing area, if we're perpendicular to the y-axis, our limits of integration have to be y values. So from here, I'm going to go from 0. And now I have to figure out, well, what's my y value for that intersection point? Well, if I'm figuring out, I know I'm at x equals 3. So when x equals 3, my y value is 9. So that's going to be my upper limit of integration. So now we're just going to go ahead and do this in the calculator. Math 9, we're going to go from 0 to 9. Let's see, I'm going to use parentheses here. 3 minus square root of x, quantity squared, dx. Okay, and we're going to get approximately 13.5. Okay, so that's pretty much what you need to know about finding the volumes of cross sections, or volumes of solids with a known cross section. When you get back, we'll be doing more practice with this, and we'll also be doing a little project. So you'll be getting lots of practice with it. So thanks for hanging in with a long video here. I hope you guys have a great break, and we'll see you when you get back.